The fourth problem asks us to find the volume of the solid with square cross-sections, illustrated in the homework, and I attempted to sketch it here, where the shape, if you were to slice it through the y-axis, or down the center line, you'd actually see a parabola, y equals 4 minus x squared. And so this parabola, 4 minus x squared, actually also shows up in the parabolas here and here if we were to look at it from the sides. Okay, and so that's going to play an important role because this rectangle here that's illustrated would correspond to one of our cross sections in the actual figure. If we were to cut a little slice out, that slice, the edge, corresponds to the little rectangle that's shown. And so that's going to play a really important part in our calculation. Alright, so since the cross sections appear when we slice it parallel to that flat bottom, this is as though we're doing a partition along our y-axis, and so we want to be able to think about how would we calculate a volume based on that partition. And so our approximation would first involve doing something like a Riemann sum. So our approximation would be given by a sum of the areas of our cross-section for some certain height, so that's our area of cross-section, and then times the thickness, delta y, where delta y is the thickness of a partition subinterval. And so what we really want to do is we want to find out, well, how do we calculate that area as a function of y? So here's where we use the idea that it's a square cross-section. Because we have a square cross-section, the distance between these edges, let's call that the side. If I have a square with sides s, the area is given by the square of that value. And so our approximation gets replaced by a sum of the side for that height squared times delta y. And all that's left is we need to figure out, well, how can we represent that side length in terms of y? Alright, so if I label these points x on the right and x on the left, then that will allow me to write my side as the value of the x on the right minus the value of the x on the left. And so what I need to do is I need to take my formula for my parabola, the curve, y equals 4 minus x squared, and I'll solve for x. So let's see, if we subtract, move the y to this side, take x squared and add it to the other side, we're able to get x squared equals 4 minus y. When we take a square root, we get plus or minus the square root of 4 minus y. And so that's where we actually get our two terms. X on the right is the positive version, and the x on the left is the negative version. And so now we know what our side formula is. We're going to add the square root of 4 minus y. That's the value of x on the right, minus the value of x on the left, 4 minus y, inside a square root with a negative sign. We'll square that, multiply by delta y. Okay, so if we look at that a little more carefully, subtracting negative, we now change it to addition, and if we notice that these are the same terms, we're actually able to rewrite our Riemann sum as a sum of two square roots of 4 minus the y value squared times delta y. And that would be our Riemann sum. So what we've done is we've imagined slicing our original figure up into lots of chunks, approximated each of those by a square, we add those up, and that would be our Riemann sum. But that's not what we really want. We want the actual volume. So what we'll do is we'll turn this integral, or this Riemann sum, we'll take a limit, and the true volume will be an integral of the side squared, 2 times the square root of 4 minus y, all squared, and the partition d delta y gets turned into the infinitesimal dy. So all that's left is I need to find the limits of integration. So I start at 0, and where do I go? I look at the parabola and the formula, and the highest value on the formula would give me a value of y equals 4. So I'm going to integrate from 0 to 4. That definite integral, as soon as I find a value, that'll be my answer. Alright, so we'll take our integral, let's rewrite it. Integral from 0 to 4. When I square the 2, I get a 4. When I square the square root, I'm left with just 4 minus y dy. So all I'm really integrating from 0 to 4 is 16 minus 4y dy. The fundamental theorem of calculus comes to a rescue, makes their life easier because we know an antiderivative, and all we need to do now is evaluate it at 4 and at 0 and subtract. When you evaluate it at 4, you get 64 minus 32. When I evaluate it as 0, I get 0. So the volume is 32. And that's our answer.